Now brace yourself, we are going to talk about versioning. We are going to see how it works. You might think that versioning is a big deal and complicated, but now that you know about the object model, you will see it's not that complicated at all. First, let's change a file. I will edit the menu text file. I will add the name of another recipe to it. Cheesecake. I'm in a cakes mood. Let's save the file, and now git status tells us that the file has changed. So let's stage it with git add and create a new commit. There. Now our working area is aligned again, and if we look at the log, we can see both commits. Let's use the now familiar cat file to peek inside this second commit. There, this commit has something more than the first one. It has a parent. The parent is the previous commit, our first commit. Commits are linked, and most commits have a parent. The very first commit is an exception. So, the commits are linked like this. Also, if you look at the hash of the tree that this second commit is pointing at, you will see that this is a brand new tree. It's not the same tree that the first commit was pointing at. It's like a different route. You will see why in a minute, but for now let's just draw a new tree here. Let's look at the content of this tree. You know how to do it by now, so I will go fast. We cat file it. We can also use just the first few digits of the hash, and Git will automatically retrieve the whole hash from the database, unless there are multiple hashes starting with these first few digits. So now we can see that the tree contains another tree, the recipes folder, and the blob menu text. Note that this is not the same menu text blob we had in the previous commit, it's a brand new blob, because this file has changed. So if we cat file it, we can see it as the new content of the file, all of it, including both the apple pie and the cheesecake. However, the tree here that lists the content of the recipes directory, this one is the same object that we already had in the database since the first commit, because the contents of this directory haven't changed. So there is no reason to create a new object. Git can just use the object that was already in the database. So here is the file structure of the object database after our second commit. The new commit is pointing to a new tree, which is pointing to a new blob, and to the same tree as the first commit. Now it's clear why this tree must be new. This blob has changed, so the content of this tree must be different because it's pointing to a different blob. As usual, if you change anything in a piece of content, then you get a whole new object with a new hash. This tree, however, it hasn't changed because nothing inside the directory changed, so Git can reuse the same object. That's one of the reasons why Git is so efficient. It doesn't store things more than once. We changed the single file, so Git stored a new blob, and in our case a new tree and a new commit, because they are ultimately pointing at that new file, so they had to change. The hashes they contain have changed. Trees and commits are really small, however, so even if they change, it's not a big deal. The process is still quite efficient. If you count the number of objects in this diagram, it's 2 commits plus 6 trees and blobs, 8 objects total. This is the current number of objects in the object database. Let's double check it. The database itself is getting a bit crowded, so instead of counting the files, let's use one of those seldom used plumbing commands, git count objects. And there you are, 8 objects, and they take a very small amount of disk space. Speaking of efficiency, you might be surprised that Git stores a new blob every time you change a file. What if I have a huge file and I only change a single line? Will Git store an entire new blob in this case and duplicate the rest of the file? Well, not really. Git also has another layer of optimizations to save more space. For example, as you keep working and adding content to the repository, Git might decide to store only the differences between the two files, or even compress multiple objects in the same physical file. By the way, that kind of stuff is the reason for those mysterious info and pack directories in the database. However, we are really talking about implementation details, and usually you can ignore them. To understand the Git model, it's good enough to think of each commit, blob, or tree as just files, separate files, that are hashed and stored in the database. At the commands level, this is how Git actually works. And then it has another layer of optimizations that are probably not interesting to you unless you're working on the Git source code. Just know this, when it comes to being efficient, you can assume that Git always does the right thing.